Hello students, welcome to the class. So today we will be seeing the theory part 11 of the chapter 6 equilibrium, in which we will be covering section 6.12 of the NCRT. Now this is the disclaimer. Our objective would be to look at the buffer solution, right? So this is our topic today, and I would suggest you to attend it very sensibly because this is a very important topic. Numericals are asked from this part most of the cases, and I will try to make it simpler as possible, right? So let's see that what is the distribution according to the NCRT. Now, according to the NCRT, this is section 6.12, as I said, and the name is buffer solutions. In this, we will see the section number 6.12.1, which is designing buffer solution. After that, we will do problems on the same topic, which is problem number 1 and 2. So these are some problems which I have crafted for you to make you understand this buffer topic, right? So first, let's begin with what is buffer. So a very simple definition is there. It says that whenever you are changing the pH of a solution and it is resisting that change, then in that case, you call that solution as a buffer solution. But remember, there is a thing in it, which is the amount of change which it can resist. In most of the buffer, which I am familiar with, resist only a small pH change. It is not that you will add a very large amount of concentrated acid or base and it will not allow the solution to change the pH. In that case, in most of the cases, it only resists a small change in the pH. So this is very important. See, it is written that it can resist changes in pH on dilution with the addition of small amount of acid or base or alkali. Now, what are the types of buffer solution? So again, the buffer solution has a property to defend the pH, and it will have a pH of itself, of course. On that basis, it has been divided into two parts. First is your acidic buffer, and here you use a mixture of weak acids and its salt of a strong base. So two things are there. The solution should contain a weak acid and it should contain its salt, means the acid salt only, the weak acid salts only, along with a strong base, means the cationic part of that salt should be coming from a strong base. So this is the thing for acidic buffer. Now there is a confusion in students' mind in most of the cases I see, is that the acidic buffer can only resist a change in the pH if acid is added. No, that is not the meaning of acidic buffer. Acidic buffer means whose pH is less than 7 and the role of the buffer is same. It will resist the pH, and in both the cases, either you are taking acidic buffer or basic buffer, it will resist change in pH on addition of acid and base both. So individually both of them are capable of resisting the change in pH of addition of acid and base. The only thing is that this acidic buffer keeps the pH check less than 7, right? Whereas if you take an example of it, suppose we are taking acetic acid, right? So I said that your acidic buffer must contain a weak acid. So you know that acetic acid is a weak one and it should contain its salt. So the salt of this acetic acid will be containing acetate ion. So see, we have taken sodium acetate, and this sodium is a part of a strong base. So this is a cation which is most probably coming from sodium hydroxide. So this given solution met up the criteria for being a acidic buffer, right? Similar to that, we can define the basic buffer. Here, instead of the weak acid, we have a weak base in the solution, and instead of a salt of a strong base, we have a salt of a strong acid. And what about the pH? Again, since it is a basic buffer, it will resist the change in pH for addition of acid and base both, and it will maintain a pH for its solution which will be greater than 7, right? So that would be named as a basic buffer. What can be the example of it? Say we have this ammonium hydroxide and ammonium chloride. Now, ammonium hydroxide is a weak base, right? And you can take the cationic part of this ammonium hydroxide, which is ammonium, and combine it with the anion of a strong acid to make ammonium chloride. So, here the strong acid is probably hydrochloric acid, which is giving its anionic part, which is chloride. So, overall, what we can say that what is a buffer solution? It is something which is resisting the change of pH in a given solution, and it will resist only a small amount of addition for a acid and alkali. Now, on the basis of the pH which it is maintaining, it is defined as acidic buffer or basic buffer. So, if it is maintaining a pH less than 7, in the range of less than 7, then we call it as a acidic buffer. And the acidic buffer contains a weak acid and its salt of a strong base. Example is acetic acid and sodium acetate. Similarly, your basic buffer would contain a mixture of weak base and its salt, and it will maintain a pH will be greater than 7. Example would be ammonium hydroxide and ammonium chloride. Can you think of more examples? Can I take another weak acid and its salt for acidic buffer? Just think of it, right? So this is a task. I'm leaving this up to you. Just think of more examples both for acidic and basic buffer, right? So this will help you to solve numerical easily. Once you are able to predict that whether the given solution is a buffer or not, and if it is a buffer, it is which one, acidic or basic, you are able to decide it, then you are good to go. Okay. Now, how this buffer help us to reduce the pH? What is the defense mechanism of this buffer? So, we'll try to understand this with the help of the same example that we have seen right now. In the case of acidic buffer, which is sodium acetate and acetic acid. So, here we are considering acetate ion alone because this is only responsible for maintaining the pH. Sodium plus has no role in it. Suppose we have a solution that contains a high concentration of the following things, which is weak acid and its conjugate base, right? Now, what you do, you add strong acid into it, and that acid is added in a small amount. Strong acid in a small amount. What it will produce? It will produce H plus ion. Then you know that your solution contains acetate ion, right? So what will that acetate ion do? It will take up that H plus and it will be converted into acetic acid. So this will be your reaction or the response of your buffer. Now the acetic acid which is formed, it is an example of a weak electrolyte. So it will not dissociate backward. Yes, there will be dissociation to some extent, but that dissociation is not significant. Suppose if H plus, which is being taken up by the acetate ion, is 10 moles, right? Then maybe you would be dissociating this acetic acid back to give you 0.0001 mole or something like that. Means the thing which is taken up by the acetate ion and the thing which is dissociated, which is given by the acetic acid, has a very large difference. So this is due to the small fraction of dissociation for acetic acid. Similarly, what will happen if you add a base? So that is interesting. So this is important to remember because student often forgets to remember the action in case you are adding a strong base to a acidic buffer. So here what will happen? Your acetic acid will react with your hydroxide ion to produce the acetate ion along with the water. Now here you can easily see that water is a weak electrolyte, right? And it will not dissociate into H plus and OH minus in significant amount. You know it very well that water has a very small ionic product, which is 10 to the power of minus 14. It clearly indicates that the dissociation of water occurs in a very small range. So, your hydroxide ion is consumed by the acetic acid, and the water which is formed is not dissociating back to give you back the hydroxide ion which is produced. In this way, your extra added H plus and OH minus are being consumed, and there will be no net change in the pH of the buffer solution. I hope this is clear to you. So this is very important to remember. How is the buffer acting? Can we see the same with the help of a diagram? Yes. See, we have your addition of OH minus in the first case. Here, the OH minus is taking us up the H plus from the acetic acid to make the H2O and releasing the acetate ion. This H2O will not dissociate back to give the H plus and OH minus in significant amount. Similarly, the acid which you are adding, that is being taken up by the salt part, which is acetate ion to produce the acetic acid. So basically, your weak acid, right? Your weak acid, which is present in the solution, it is acting as a resistant for the base addition, whereas your acetate ion, which is the salt part, it is acting as a resistant for the change in pH due to the H plus. So this action is very important to understand. Then and then only you will be able to solve the numerical. Okay. So with this, let us try to quantify, because the most important part is that how do we quantify it? We know that it maintains a pH. It maintains a pH. If it is acidic buffer, it will maintain it below 7. But the question is that what is the pH which it is maintaining? What is that accurate value? Of course, that value will depend upon what? It will depend upon the concentration of the salt and the concentration of the acid. But what is the relation between the pH and the concentration of salt and the concentration of acid? Let's derive it. In that derivation, you need to know some important terms. We will discuss it. Say we have a weak acid and a conjugate base, Ha and A minus are the representation of those in a solution. Now, we know it very well. The Ha will react with water to form the H3O plus and A minus. So this is occur up to a very small extent because it is a weak acid, but still it will release some hydronium ion. Now, if you try to write the expression for the acid dissociation constant for the weak acid, which is written as Ka, we can write it as the concentration of the product, which is H3O plus and A minus, divided by the concentration of the acid, which is Ha. Further, we know it very well. What are these terms here? H3O plus is the concentration of hydronium ions, and your A minus is the concentration of conjugate base. Whereas in the denominator, we have the reactant, which is acetic acid, whose concentration is written there, which is a weak acid. So this is your dissociation constant, right? We know it very well. How do we write it? And you must remember that the concentration of water is very excess and its change is not that much significant. So we consider it as constant. And the equilibrium constant multiplied by the concentration of water is giving you this acid dissociation constant. Further, what we will do? The second thing which you should know, if you know this acid dissociation constant, is your H3O plus concentration. So what we can do, we can just rearrange this equation, above equation, to give you the concentration of your H3O plus, which will be Ka multiplied by Ha concentration divided by conjugate base concentration. Further, you will take a negative logarithm on both sides. And remember, the base will be 10. If you will do it, what will happen? You will get minus log of H3O plus. Then we have minus log of Ka. Next, what we have? We have minus log of Ha divided by the A minus concentration. Here you should notice one very important thing, which is after taking log, your multiplication turns into addition. So now you have to add minus log Ka and minus log Ha by A minus, and therefore you are getting this result. Now, are we familiar about these terms? Do we know what is log H3A plus along with this negative sign? Do we know what is minus log of K? Yes, we know it. So we will replace those things. Therefore, your pH will be now pKa plus log A minus by Ha, where your A minus is within the square brackets for representing the concentration of conjugate base, and Ha is the concentration of the acid. So this is your equation for calculating the pH. Now, this equation that you got is a very famous one. So this equation is called as Henderson-Hasselbalch equation. If you are defining it for acidic buffer, like the way you have defined it in the previous case, we can just write it in a descriptive manner. How? So we know that your acetic acid, or sorry, your weak acid is dissociating in this way. Then, if you just take this previous equation, pH is equals to pKa log A minus by HA, then you can write it as log of conjugate base. So what is this A minus? It is your conjugate base. So this is just a descriptive way of writing your previous equation. In the denominator, we have this HA, which is acid, right? So pH is equals to pKa plus log conjugate base by acid. So this is your general formula to calculate the pH of an acidic buffer according to Henderson-Hasselbalch equation. Here, you know it very well that A minus is what? It is the concentration of conjugate base and HA is the concentration of acid. We have already defined this, but still you should remember this equation as whole. Now, can we derive similarly it for the basic buffer? Yes, we can do it. So, try to derive this formula. I am giving you the final formula. You will follow the same steps. There is a very minute change which will be according to the basic buffer because you are doing it for the basic condition. How we'll write it? So if you are considering this reaction for a basic buffer where your base is B and it is reacting with water to give you BH plus along with the hydroxide ion, then you can write that POH will be given by pKb plus log conjugate acid by your base, where conjugate acid concentration is in the numerator and the base concentration is the denominator. Here, the BH plus, what it is? It is your conjugate acid concentration and your B under brackets will be your base concentration. Remember, what is the difference between the acidic buffer formula and the basic buffer formula? Instead of finding your pH, here we are considering it for the POH. Instead of pKa, we have this pKb, and instead of conjugate acid by base concentration ratio, we have this conjugate base by acid concentration ratio in case of acidic buffer. So you can remember this in this way. If you remember the initial formula or the parent formula, you will remember both the cases. I hope this is clear to you. So these two formulas are very, very important. If someone asks you, can you calculate pH from here? Yes, it's very simple. We know it very well that pH plus POH is equals to 14. Therefore, POH will be nothing but 14 minus pH. So you will subtract whole of this thing which is equals to POH from 14 to give you your pH of the basic buffer. Now, moving on further, we will look at some aspects of this reaction, of this equation, not this reaction, of this equation. Suppose we again took this equation 6.39 of the NCERT. Then what we can do is we can equate both of the concentration, which is we will take the same concentration of conjugate base and your acid. So you are taking the same, so you can say that in a way you are taking the same concentration of salt and your acid, right? So you are taking the same concentration of salt and acid. If you will do so, what will happen? Your extreme term, which is log A minus by HA, that will be reduced to log 1, and further you know that log 1 has a value of 0. So your whole right term will be equals to 0. Therefore, what you can say, your Henderson-Hasselbalch equation can be written as pH is equals to pKa. So this equation or this thing is only followed if you have the same concentration for the acid, which is weak acid, and its conjugate base of strong acid, strong base, right? So this is very, very important to remember. Can we move to a generalization here? Is it possible? Can you see a thing here? which is your whole thing is your whole pH, I would say, is totally dependent upon this ratio. Now we will do this same thing. We will try to define it for the ratio, that what is the importance of this ratio. Importance of this ratio. For that, we will take an example. Your example will be a ammonia buffer. What will be present in the ammonia buffer? Try to think of it. Meanwhile, I am listing the technicalities of this solution. So the pKa for ammonia is 9.25, and the buffer from ammonia base and the ammonium chloride with equal molar concentration. So here you have the equal concentration for ammonia and your conjugate acid. So you can write your Henderson-Hasselbalch equation as pH is equals to 9.25 plus log A minus by HA. Now, if they have a equal concentration of A minus and HA, then your pH will be equals to 9.25. Isn't it? So that will be obvious. This will act as what? This will act as a thing where your pH is a constant one, not a variable. Now, all of this is happening because your pH is not dependent upon the individual concentrations. Rather than it is dependent upon the ratio. Suppose in the solution, if you are adding water, will its pH change? No, because the concentration of both A minus and HA are changing in a way. So their ratio will remain same. And if your ratio will remain same, you know it very well from your previous discussion that your pH is not affected in any way. Got it? So this is very important to remember. A very important line is here, that your pH of a buffer solution will never change upon dilution, because your A minus and HA concentration have a constant ratio upon the changing of your what? Changing of your concentration for both. So you can finally say that pH of a buffer solution only depends upon its ratio and not upon the absolute concentration. Got it? I hope this is clear to you. Now moving on further, we will do a question on the same. You have to calculate the pH of a buffer solution which contains 0.25 acetic acid and 0.40 sodium acetate, and that whole thing is being kept in a 1 liter volume. You already know the value of K, which is 1.8 into 10 to the power minus 5. Now you have to simply use the formula to calculate the pH of this given buffer solution. How you will do it? So first what we will do is to write the things which are already given. So you are given with the concentration of the acetic acid, which will be 0.25 molar. Then we have the concentration of the sodium acetate, which is 0.40 molar. And we have the value of K, which is 1.8 into 10 to the power minus 5. Further, what is the concentration of conjugate base? So this conjugate base will have the same concentration, which will be the concentration for the salt, because salt is a strong electrolyte. It will dissociate completely, and therefore your each mole of your sodium acetate will give you your each mole of the acetate ion. So the concentration of the acetate ion is equals to the concentration of the sodium acetate, which will be 0.40 molar. Further, if you want to calculate the pH, you first have to calculate the pKa, because here we have the value of Ka and not the pK. How can we do it? So pK is nothing but minus log of K, therefore minus log of 1.8 into 10 to the power minus 5. So don't worry, in your exams you will be given with this value of log. So you if you want, you can just see this in your calculator. This value will come out to be 4.74. So the pK is now 4.74. Now if you know the pK, you know the concentration of acetate ion, and you know the concentration of acid. Can you calculate the pH? Yes, because the formula which is used for the calculation of pH, it is equals to pKa plus log the concentration of conjugate base divided by the concentration of acid. Further, your conjugate base is acetate ion and your acid is acetic acid. Just put the things that are already been given and the thing which you have calculated, which is pK 4.74. If you do it, you will get it as pH is equals to 4.74 plus log 0.40 by 0.25. So this will be equals to 4.94. So this is your final answer. So the pH of this buffer solution is 4.94. Can I ask you whether this buffer is a acidic or basic buffer? Yes, you can answer it. It's a very simple question. Your buffer will be a basic buffer, acidic buffer, sorry, because your pH is less than 7, right? Moving on to the next question. How many moles of sodium formate must be added to 1 liter of 0.50 formic acid to prepare a buffer solution with a pH of 4? The Ka for formic acid is 1.8 into 10 to the power minus 4. So here you are trying to design a buffer. Okay, we have not talked much about this, but I will try to make you understand this designing of buffer with the help of this question. So what is given initially? You are given with a solution of acetic acid. Now you have to see that what amount of sodium formate you will add to make it a buffer whose pH is 4.00. So it's very simple. It is just a way to ask the question directly from the formula. Why? Because in this case you know the pH and you don't know the concentration of conjugate base. As simple as that. Now your question should arise whether it is an acidic buffer or a basic buffer. So see, we have two parts here. So one thing is already present and one you have to add. The thing which is present is your formic acid, means it is a acid and it is a organic one. So of course it will be a weak one. What about the other part? So this question is adding a concentration of sodium formate. Now sodium formate is nothing but a conjugate base for the formic acid along with a part where the cation is coming from a strong base. So this is one way, and the most simplest way would be looking at the pH. See, the pH is less than 7, so this is a acidic buffer, right? So let's see how we'll solve it. First, you will list what is given in the question. So that is the most important part. What are the things that are given? You are given with the concentration of acetic acid 0.50 molar, then Ka, which is 1.8 into 10 to the power minus 4, and pH, which is 4, and volume, which is 1 liter. Got it? So the one tricky part is there. So I would say not a tricky part, because here the volume is kept to 1, so you don't have to worry much. If your volume is being changing, then you have to worry about it, right? So first you have to calculate the concentration. Then if you know the concentration, you know the volume also, and further you have to calculate the moles accordingly. But here, since the volume is kept to 1 liter, you don't have to worry about it. We will see it. Similar to the previous case, our first task is to calculate the pKa. So using NCERT equation 6.31, we can write pKa is equals to minus log of Ka, which is minus log of 1.8 into 10 to the power minus 4. It is given in the question. Now put this value, you will get it as 3.74. Again, my suggestion would be you don't have to worry about this log value. It will be given in your question in case of your exam. Further, our next task is to use the formula of your what? Henderson-Hasselbalch equation. What kind of pH do we have? We have a pH for an acidic buffer. So the formula would be pH is equals to pKa plus log conjugate base by the concentration of acid. Now your conjugate base is formate and your acid is formic acid. We have already calculated this value of pK in the previous part, 3.74. Just put it here, and we are already given with the value of pH and acetic acid. Now on solving this ratio, what you will get? 4.00 minus 3.74, then log concentration of the conjugate base divided by the concentration of acetic acid which is being put, which is 0.50. Now just evaluate this further. This will be 0.26 is equals to log concentration of formate ion divided by the 0.50. Now what you have to do is to simply simplify this equation to get your answer. What will happen? So we have this thing. We will take anti-log on both sides. Means you will be taking 10 to the power 0.26. Now your question should arise, why are we taking 10 to the power? Because we have taken the base 10. Therefore, for anti-log, we will take the power onto 10. Now 10 to the power log something will give you that same value. So 10 to the power log concentration of conjugate base divided by 0.5 will give you concentration of conjugate base divided by 0.5. So 10 to the power 0.26 is equals to concentration of conjugate base divided by the 0.50. Further, if you evaluate this, again you don't have to worry about 10 to the power 0.26. It will be given in a question. So this will be equals to 1.82. Now next, your only thing is to calculate this formate ion concentration. So cross multiply it. What will happen upon cross multiplying this thing? It will give you the value as 1.82 into 0.50. So this value will be 0.91 molar. But the question is saying that you have to calculate the moles of sodium formate, not your formate ion. But we have talked about this in the previous question, that your strong electrolyte dissociates completely and salt is a strong one. So each mole of formate ion will give you each mole of formate, which will be coming from each mole of the sodium formate. Therefore, what we can say, that moles of the formate ion is equals to moles of the sodium formate. Therefore, your correct answer will be, for the concentration of the formate sodium formate will be 0.91. But here you have to calculate the moles and not the concentration. So mole is nothing but molarity into volume. So molarity is 0.91 and volume is already given as 1. Therefore, your final moles of sodium formate will be 0.91. Is this clear to you? So if you want to design a buffer solution of pH 4, which is already having 5 molar concentration of the formic acid in 1 liter of the solution, and you already know the pKa, which is 1.8 into 10 to the power minus 4 for formic acid, then 0.91 moles of sodium for formate ion, or I would say sodium formate, should be added to the solution to make this buffer of pH 4, right? Now we can just summarize all of today's class. So we started with the buffer solution. We said that anything that resists the pH is called as a buffer solution, and it can be of two types. It can be a combination of weak acid or conjugate base, which is your acidic buffer, or a combination of weak base and a conjugate acid, which is a basic buffer. Then what we have? We have our action. So it can neutralize both H plus and OH minus through equilibrium reaction. So if you are talking about the acidic buffer, then in that case, your formate ion neutralizes the H plus and your acetic acid neutralizes the hydroxide ion. So you have to choose your acid base pairs accordingly with a certain pK to design a buffer of a certain pH. Next is your Henderson-Hasselbalch equation, which will help you to design this buffer solution. So the quantification for acidic buffer is pH is equals to pKa plus log conjugate base by acid, whereas your basic buffer is POH is equals to pKb plus log conjugate acid by base. So this was all for today's class. I hope you enjoyed the session. Thank you for joining it.